Hello everyone. Today we are going to present a RIAPS application for microgrid energy management. RIAPS, standing for Resilient Information Architecture Platform for the Smart Grid, is a software framework for developing distributed control applications for smart infrastructure. This energy management application was created by North Carolina State University and Vanderbilt University in collaboration with VMware, with support from ARPA-E. First, let's have a look at the application architecture. The application assumes a microgrid controlled by 4 different RIAPS computing nodes: the building node, EV charger node, battery node, and coordinator node. The building, EV, and battery nodes send and receive messages from the coordinator node. They also have the ability to communicate directly with their power system devices: the building energy management system, the EV charger, and the battery energy storage system. Through the node's communication and coordination, we want to realize the following objectives in this application. First, we want to predict the power consumption of the EV charger and the building for the next 24 hours. Second, we want to optimally allocate available power to the EV charger and the building with the help of the battery energy storage system. To realize these objectives, each node must perform its individual functions. This application and its demonstration assume a single building, EV charger, and battery. However, our system is scalable to any number of these components, allowing individualized predictive models for different buildings and EV chargers. The building node and EV node are similar. They take real-time power measurements from the building energy controller and EV charger. Using this real-time power measurement as input, they use machine learning models to predict the power demands of the building and EV charger for the next 24 hours. Lastly, the building and EV nodes execute power curtailment as commanded by the coordinator node. The battery node takes real-time state of charge measurements from the battery energy storage system. The battery node also takes commands from the coordinator node to charge or discharge the battery. The coordinator node collects all the data and stores them in a database. Further, it solves an optimization problem to allocate power among the building, the EV charger, and the battery for the next 24 hours. Now let's have a look at the machine learning model we developed for load prediction. The model has an encoder-decoder structure. Both encoder and decoder use LSTM networks. The encoder LSTM takes the historical input and compresses it into a context vector. The decoder LSTM uses the context vector and some calendar information as input to predict the power usage for the next 24 hours. Once the predictions are ready, we formulate the optimization problem of allocating available power among the building and the EV charger. The optimization problem uses a quadratic cost function to minimize the difference between the allocated power and predicted power usage. The cost function can have different weights for different nodes and different time steps. The constraints of the optimization problem guarantee that the battery will not be overcharged nor over-discharged. Further, it guarantees the power imported from the grid will not exceed a given power limit. This grid power limit depends on the mode the microgrid is in. In predicted mode, this power limit is set to the prediction made 24 time steps ahead. With a 1-hour time step, this means the power is purchased 1 day ahead based on the prediction. In available mode, the grid power limit is set to a user-defined constant. This mode emulates the situation where the grid power is set by the utility. Next, let's see the entire application flow. During each time step, the building and EV node make predictions for their power usage for the next 24 time steps and send the prediction to the coordinator node. The battery node also reports its current state of charge to the coordinator. After receiving those messages, the coordinator node first purchases power from the utility for 24 time steps in the future, based upon the prediction. Then, it solves the optimization problem and dispatches the allocated power to the other nodes. After receiving the allocated power, the building node and EV node will perform load curtailment if necessary, and the battery node will execute its power command and update its state of charge for the next time step. If we view this process over time, it should look like this. The prediction and the optimal power allocation are calculated for the next 24 time steps. The grid power purchase is made for the 24th time step. Only the commands for the immediate next time step will be executed.
A graphical user interface was built for this application. The top left part of the GUI is the control panel where we can change the mode of the microgrid app, set the grid power limit, and assign optimization weights for the building and the EV nodes. The 5 plots show the grid power, building power, EV charger power, battery power, and battery state of charge. These power values are in kilowatts, and the state of charge is in kilowatt hours. In the building power and EV charger power plots, there are 3 curves: the predicted power, allocated power, and actual power. The battery power plot has 2 curves, allocated power and actual power, because we control the power level of the battery instead of predicting it. We will now demonstrate the running application. The designed time step for the application is 1 hour. For demonstration purposes, we scale time, so 1 hour of simulation time spans 12 seconds of real time. Therefore, the plots will update every 12 seconds, as though the system has been running for 1 hour. The vertical white bar in each plot is placed at the current time step. To the left of the white bar are the historical data, and to the right are the future time steps showing predicted data. Right now, the application is running in predicted mode. The power available from the grid is purchased 24 time steps ahead, based on the predictions from our machine learning models. When there is a difference between the microgrid load and purchased grid power, the battery absorbs that difference by either supplementing or storing grid power. Because the prediction is highly accurate, the power purchased from the grid can satisfy the loads in the microgrid. This is shown in the grid power plot, as the available power purchased from the grid is very close to the total power dispatched to the loads. The battery state of charge is limited from 20% to 90%, as was formatted in the optimization problem. Assuming a 1000 kilowatt-hour battery, these limits are 200 and 900 kilowatt-hours. Now, we switch the microgrid control mode into available mode. In this mode, the power available from the grid is set by the user through the sliding bar in the GUI. The power available from the grid is currently set to 800 kilowatts, which cannot meet the needs of the building and EV charger. To supplement the shortage of power from the grid, the battery starts to discharge until its state of charge reaches 20%. If the power from the grid and the power from battery combined cannot meet the needs of the microgrid load, the algorithm will allocate less power than the predicted value. In this case, the building node and EV node will curtail their consumption in order to meet their allocation. From the building power plots, we can observe that the allocated power is much less than the predicted power due to the power shortage. Next, we increase the power available from the grid to 2000 kilowatts. In this case, the power from the grid can satisfy the loads in the microgrid. The excess power from the grid will be allocated to the battery for charging. We can observe the battery's state of charge increases until it reaches 90%. In summary, with this application, we show that our machine learning model can accurately predict the power usage of the microgrid. Our energy management algorithm allocates the available power to different nodes and operates the battery energy storage system optimally.